Okay, let's get started. This is the last class of this semester. I'd like to congratulate everybody for keeping along, doing the best you can, and doing all the practice sessions every week, and the 2 projects as well. So I hope everybody had a good time. The last topic is neural ordinary differential equations, or neural ODE in short. So let's get to it then. So in order to understand neural ODE, we have to first understand what ODEs are. So a lot of people probably had gone through mathematics for engineering, or in Korean, 공학수학. So we did learn some ordinary differential equations in that class. But still, like for some of you who might have not gone through that class or do not have the background knowledge, we will go through ODE preliminary knowledge first and then move on to neural ODE. So in ODE, we'll first talk about first order ODEs, because there can be like high order ODEs as well. So first order ODE, we'll talk about that, and then we'll define initial value problem, or in short IVP. And then we're going to move on to how to solve a first order ODE, or how to solve an initial value problem, IVP. And then after that, we'll move on to neural ODE. So it's the entire class today is going to be a bit mathematical, but it's all very like simple stuff, to be honest. So hope you guys follow along. So ODE, right? So first order differential equations, DE. It's any problem. It is defined as any problem formulation that follows this form. So it means that so dy dt is y prime. So y prime equals some function of y and t. So t is the one that is doing the differentiation with respect to. So usually it's time, because differential equations were first, or I'm not really sure about the history, but it's usually very heavily used in like classical mechanics, shooting a cannon or dropping something in the air or something like that. So t is usually time, and y could be a velocity, or it could be like a position, something that changes over time. So the change over time, which is y prime, or the rate of change over time, is defined by some function of y and t. So that's first order differential equations. And of course, second order differential equations will involve y double prime, and third order will involve y triple prime, such and such. Right. So what this means is this equation means is that we don't know how to calculate y directly. So for example, if we are to, let's say that we are trying to measure the velocity of a ball, like we drop a ball in midair, so it's a free falling object, and we'd like to calculate the velocity of the ball at certain time t. But we don't know how to do that. So we don't know the solution. But what we do know is we know how to calculate the change of y. So this is the change of y over time. So what we know is that what we don't know is the velocity at time t. But what we do know is how velocity changes over time, or the rate of change of velocity over time. So this is what this. So yeah, that's what this first order differential equation means. So there are a lot of types of first order differential equations. This is like linear differential equations usually take the form like this. So y prime plus some function of time, pt, multiplied by y equals gt, some other function over time. So that's usually what we call a linear differential equations. There's also something called separable differential equations, which looks like this. So all functions related to y, the one that we're interested in, is multiplied to the y prime, the rate of change, and all the functions regarding time t is all in the other side. So it's separated. And Bernoulli differential equations looks like this. So there's a high order y variable, y like to the power of n, something like that. But they are all like special cases of this equation. So yeah, like this. So what we have here is you can simply take this and move it over to the right hand side, and we get this. So y prime equals some function of y and t, which is exactly this. Same deal with here, separable dE. You take this and move it over here, you get this, which is also another some function of t and y. Again, Bernoulli differential equation. You take this, put it over here, and you get this, which is again a some function of y and t. So it's all special case, three different special cases. So yeah, so example. So just like, you know, when we talk about abstract concepts like differential equations, so to me it always helps to think about like concrete examples. So we're going to talk about free falling objects. So we drop something in midair, and we want to know the velocity. We want to know the velocity of a falling object at time t. So we don't know. So as I said, we don't know how to calculate velocity at time t. So we don't know we don't know what vt we don't know the function vt. But what we do know is we do know v prime t, which is dv dt. So we do know this. We don't know this, but we do know this. So how do we do this? So, oh, actually, yeah, that was a question. Sorry about that. So we don't know this, but do we know how the velocity changes over time? So do we know this? Because in order to solve this in a differential equation paradigm or frame, even if we don't know this, we still need to know this, right? So that's whole idea behind differential equation. And in fact, it turns out that we do know how velocity changes over time because we do have access to Newton's law of motion, or specifically second law of motion, which is F equals ma. So we're going to use that to derive how to solve for Vt. Right, so F equals ma. And a can be rewritten as a, which is an acceleration, is a rate of change of v over time. So it's instantaneous change of the velocity. And so we can plug this here like this, and then we get this. So ma, and which is equal to the force. And force can be written as a function of velocity and time. So force is something that could change over time and the velocity of the object. So let's, we're continuing on the Newton's law of motion. So we have this. If we do not take into account the air friction, which is 공기저항, so if we do not take that into account, then this is simply, F is simply a constant. It doesn't change over time. It doesn't change depending on the velocity. It's just the gravity constant, which is 9.8 meter per second squared, multiplied by the mass m. So it's a constant. So F is a constant. But if we do take into account the air friction, then let's just say that the air friction. So if air friction is a force that applies in the opposite direction. So if the ball is falling this way, then the air friction is applied this way, and the force of the air friction is here it's gamma v being the velocity, and gamma is some friction constant. So it's like, so the minus is to account for the opposite direction, and gamma is the friction constant, v is the velocity. So semantically it means that the faster something falls, the more powerful the force will be, or the more powerful the friction will be. Actually, there's a typo here. It should be friction. So the more powerful the friction will be, and it'll slow down the object, or it'll work in a manner that slows down the object's velocity. So all right, so we have this equation, and we can rewrite this in this format. We just divide both sides with n, and then and this is a constant. This is a constant. Let's just say this is also a constant. So everything is a constant. So besides v, except for v, everything is constant on the right hand side. So g equals 9.8, and let's say that gamma is let's say that m is just 1, so like it's 1 kilogram, 1 kilo, and gamma is some constant like this. So the final differential equation of the free-falling object with air friction accounted for is this. So we have, and so it is like the differential equation is some function of v and t. And here there's no t here, but there is v here. The v is here. So before we actually start to solve this so given this, we want to solve this eventually, right? So we want to be able to tell the velocity of the object at certain time, like maybe 5 seconds later or 10 seconds later, 15 seconds later, something like that. But so let's kind of work backwards actually. So what if at certain time t, velocity was 50 meters per second? So we plug in 50 meters per second here, then what would happen? Then we would obtain the rate of the gradient, basically the tangent, or the rate of change of velocity at time at that instant, the instant being when the object's velocity is 50 meters per second. So it turns out that if you plug in 50 here, then it's exactly 0. So that means when the object's velocity is 50 meters per second, there's no change to velocity. So here it's, so this is time axis, this is time axis, and this is a velocity axis. And it means that as time goes by, when you start, when your velocity is 50 meters per second, it won't change. It'll just stick to the same velocity over time. So this red arrow, the red arrow represents the red arrow. Each red arrow represents dv dt at that time step. So it's like this is the let's say here. So here dv dt when t equals 1. So, but when v equals 50, they're all 0 anyway. So it means that v, probably 50 meters per second, is the equilibrium. It's where when the gravitational force and the air friction cancels each other out. So there's no more like change to the velocity. So you can generalize this. So if your velocity is 80 meters per second, then that means that for example, let's say, I mean, going back, so 50 meters per second is the equilibrium velocity, then everything else will, so if your velocity is like higher than 50 meters per second, then it'll converge onto 50 meters per second. If your velocity is like below 50 meters per second, then it'll increase towards 50 meters per second, right? So that's why the gradients will always work towards like this. It'll work towards 50 meters per second, like this. So this is called the vector field. So it's a vector field of this particular differential equation. So it's just simply what you're doing is you're just evaluating this value at each time step, but the time step actually doesn't matter because this value doesn't change over time, only changes depending on the velocity. So you just have the same you just have the same gradient or the same slope across all time step. As long as it's 80, it's all the same. As long as it's 20, it's all the same. It doesn't change over time. It only depends, your gradient or your slope only depends on the velocity. So anyway, that's how you draw the vector field. So we can just follow the velocity. So once you have the vector field, you can just follow the trends to see how the velocity changes over time. So if your initial condition, which is your starting velocity, like even if you drop something in midair, its initial velocity could be, could be like 20 meters per second. Like you can throw your object downwards to the ground, or actually maybe you can throw your object upwards to the sky, and then it'll at some point reach 0 and then come back down to the ground, like something like that. So the initial velocity actually matters. And depending on where you start, if you start at 80 meters per second, then it'll slowly work towards its way until it reaches 50. And if you actually just just softly release the object to the ground, like your starting initial condition, your starting initial velocity being 0, then it'll start increasing the velocity and slowly until it converges to 50. So that's how you actually use the vector field. All right, moving on. So actually, once we have this, we can actually analytically solve this, which you can obtain this particular value. So this differential equation, which is obviously a linear differential equation, first order, it's actually relatively easy so that you can analytically solve this. So like intuition being that if your dv dt equals some v, then that means that, you know, the derivative of some variable takes the same form, basically. So that means that your variable would look like something like this, basically. Actually, not t. So it would. Yeah, actually, it does look like, yeah, it is t. Yeah, et. So I mean, think about it. Like if you differentiate your function and you still obtain the same form, like that, this is what is happening here. There's some constant over here, but the variable still stays here. So you differentiate your variable with respect to time, and you still get the same form, the same variable form, which indicates that it's probably some, you know, exponentiated form, basically. So you can take that intuition and then work your way backwards, and then this is what you get, actually. So you can analytically solve this differential equation, which looks like this. And there is a unknown constant c. So there's c here, which is unknown because we didn't specify the initial condition. So we need an initial condition. So like whether your v0 is 20, v0 is 80, you need to know this and then plug that in and then work your way towards defining the specific value of c. So this set of problem, where you have a differential equation and initial condition, this combination is called initial value problem, IVP. So you need to have this, and you also need to have v0 defined to some value, and that's how you get IVP, and that's how you end up with a specific solution, not a general solution. This form is a general solution because it has an unknown constant c. All right, so that was the primer for first order differential equation. And yeah, so if you specify your initial condition, initial velocity to be 48 meters per second, then you can work your way towards getting c to be 2. Right. So that's your final solution. So if this means that if your initial velocity is 48 meters per second, then at certain time t could be like 5 seconds later, 10 seconds later, 15 seconds later, you can just plug this value in to calculate the exact velocity at that time. So that's your solution. So we're going to move on to the numerical solution now. This was analytical solution. But assume that what if we can solve this analytically? So we have to solve it numerically. Like, for example, if your differential equation, first order differential equation, is not linear, it's not separable, it's not Bernoulli, it's just some weird form that's hard for you to analytically solve, then what you have to do is just solving it numerically. So you have some differential equation that has a very complex form function on this side, then the only thing you can do is numerically solve it, or you can actually approximate it to a more manageable form, but that's just another other topic. So this is all, this is computer science, basically. So it's mathematics, it's machine learning. So numerical solution is what we are actually interested in. So let's just assume that this is no longer analytically solvable. So we're going to turn to numerical solution. So we have what's called a Euler's method. So Euler's method is the oldest numerical algorithm for solving ODEs, basically. So we have an IVP, and we have IVP being, we have an initial value problem, we have the differential equation, the derivative, and we have the initial condition of y, and the slope of the solution at t0, which is the initial point, would be this. So we have a initial at this. We actually know, we do know this value. This value is a ground truth value. This value was given to us, and at time t0, we can evaluate the slope at time t0, which you can simply do by plugging this value and this value here and here, right? So here. So that's your slope or your gradient at t0. And you can actually draw a tangent line to the solution at t0, which is simply just this. So this is a tangent line. You have y0, you have the slope, and you have the t0 here. So this is all you need to have. So if you have, like, this is your y, and this is a bad, this is your y, this is your t, and all you need to do is you just need to have the slope in order to draw a tangent line, which will look like this, basically. So let's say that the red line is the true trajectory of your y, which is your target variable, like velocity. Like y is your velocity. So it changes over time. But what you are interested in now is that you can't exactly calculate yt. So you don't have the analytical solution. You don't have the analytical solution of yt. But so you're trying to numerically approximate it. And your first step towards that is calculating the tangent line at t0. So this is your t0. This is your t0. And you have the slope. So you have the slope, which is ft0y0. And this is your tangent line. All right, this is your tangent line. Like, this is your tangent line. And obviously, you can assume what I'm going to do next. So this is exactly like gradient descent. So you take some small step. So I'm going to erase all this. I'm going to erase all this. And let's just use red. So you're going to take some small step towards your tangent line, and then that becomes your next solution, or your approximated y1. Or so here, actually, in this figure, they moved all the way to here. So they took a pretty big step towards this tangent line, along this tangent line, which is T1. So it's a pretty big delta, which is not a good idea, by the way. So anyway, so you took a pretty big step, like delta t worth step, delta t amount of step along the tangent line, and so you are here now. So your approximated y1 hat, and the true y1 has some error here. So there's certain error here. This is the error. So this is the error. And then what you do is next you calculate y. What you would do is you take ft1 y1 hat, which is the approximated solution, and then take another tangent line, which would probably look like this. Oh, actually, tangent line, I should draw it in blue line. So this is your next step would be like another tangent line like this. So this slope is what? It's T1 y1 hat. And then you take tangent line, and then you move on to T2. You take another big step, T2, and this becomes your new solution. This becomes your new solution at T2 y2 hat, and this becomes your error now. And so you can see that the error has increased. So apparently, a numerical solution will always involve some amount of error. So the key is to actually minimize the error. And you can obviously think of a way to do it is simply using smaller steps. So delta t, you want to use like as small delta t as possible in order to minimize your error. So yeah, so this is the algorithm for using a fixed step out. So Euler's method is a fixed step algorithm. You need to define the delta t first. So you need to define delta t is defined or is fixed. Delta t is fixed, and you need to fix it actually. user given. Delta t is fixed. So it's simply you just take some step towards this guy, and then take this guy, take another step, and as you can see, the error increases over time. So the at t, like the last time step t, the true yt is here, but your approximated yt is here. So there's some error there. So yeah, you just repeat this process over and over and over again. So if you put this into a more like succinct form, then it looks like it looks like this. So your final solution at time step t, or like time step large capital T, is your initial condition plus the integration over time using your dynamics function or the derivative function, because this is also given to you. This is given to you because it's a differential equation. So you have access to this, you have access to this. So you just need to numerically solve it. The integration is numerically solving it, basically. If you have analytical solution, you can just analytically solve it, like in the free-falling object example. But since you don't have analytical solution, you need to programmatically solve it using ODE solver. So ODE solve being Euler's method in this case, Euler's method. And the arguments for this program is your initial condition, your derivative function, dy dt, and your starting time step or starting time point and the ending time point. And also, actually, I forgot, but you need to define delta t as well, because it's a fixed. This is Euler's method, so you need to define your delta t, like how fine-grained step you want to take. As I said, if you take like smaller delta t means higher precision. Right, so this is where the things get interesting, because we're now using machine's power to do this integration for you. So yeah, so in theory, if you just have vector field and an initial condition, vector field being just dy dt, then you can solve any differential equation with the power of the computer, actually. So we can numerically solve the problem with a computer. There are a lot of methods other than just Euler's method. Euler's method is like the oldest, the simplest, most naive method for numerically solving differential equation. But there's something called the Runge-Kutta method. I'm not really sure how to pronounce this, but I'm just gonna call this RK method. So it's an RK method, and it provides better precision than Euler's method, because what it does is so you have IVP. Initial value problem, you have the y prime and the initial condition. So Euler's method is just simply doing a for loop over this, just repeating this over and over again, which is your next predicted solution is your current predicted solution plus h being the delta t, some small time step multiplied by the dynamics or the gradient or the slope. But Runge-Kutta, especially in the fourth order form, it's not as simple as this. So you have this here compared to this guy. It's way more complicated. So taking a small step is more complicated than just Euler's method, and it consists of 4 different parts. So K1 is just simply Euler's method. So you just take this function here, you just take it and plug it in. But the K2 is now K2 depends on K1. K2 depends on K1, as you can see here, right here. And then K3 depends on K2, right here. And K4 depends on K3. So it is iteratively, like kind of recursively going a bit further and further and further based on its own prediction, and then averaging them out. You can see it's averaging, like what it's the ratio, the average is 1, 2, 2, 1, 1, 2, 2, 1, and that's why you divide by 6. So that's basically how you do Runge-Kutta. And graphically, it's this is K1, and then this is K2. This is K3, and this is K4, and then you average them out dividing it with 6, and then that's how you get this particular. That is how you reach from here to here, and you can see that it has a very low error actually. So let me just erase some of this. So the blue line is the ground truth line. So blue line here is your true y t1, and the green line is your predicted y1 based on Runge-Kutta fourth order. And you can see that the star here has very small error, very small error, like almost minuscule error. So that's the power of Runge-Kutta. But obviously, it'll take more time than simply Euler's method, because it is doing Euler's method basically 4 times in a single step. So there's K1 to K4. So that each involves the similar form of Euler's method. So it's 4 times as slow as Euler's method, actually. But it's way more precise. So there's a trade-off. So if you have a powerful computer, you can use RK4. If you have a slow computer, you can just use Euler's method, actually. Yeah, this is the comparison between RK4 and Euler's method. And your dy dt, your derivative function, is y sine t squared, basically. All right, it's y sine squared, which is the orange line. So the orange line is right here, right? Yeah. That's the orange line. And Euler's method is the pink line, which is doing pretty bad. So initially the error is like this much, and in the end the error is like this much. This is the error, which is doing a bad job. But Runge-Kutta here, which is the gold line, yeah. Runge-Kutta here is doing a very good job. So even at the last time step, the error is only like this much. This is RK4 error. This is Euler. Oops. This is Euler error. There are some other methods. There's like Hund's method and Euler's method with, I'm not sure. This is actually all German, so I'm not really sure what they mean. But at least I know that this is Runge-Kutta and this is Euler, and this is exact solution. Right, yeah, so that's the power of Runge-Kutta, so RK4. So if you, in most cases, you should use RK4 instead of using Euler's method. Right, moving on. So there's a long history of ODE solvers. So there's a lot of ODE solvers, actually. And it has a long history in mathematics, both in mathematics and physics, because as I said, ordinary differential equations are used not just in classical mechanics, but also in electronic circuits, like RLC circuits. You know that RLC circuits can be formulated in second-order differential equations, right? So a long-standing history, and it means that there's a lot of like advanced methods out there, and they guarantee they guarantee some level of performance. So in short, there are 2 big categories, which is fixed step size solvers, and which another is adaptive step size solvers. So these are some of the well-known fixed step size solvers, and these are the well-known adaptive step size solvers. We've already looked at Euler's and Runge-Kutta. So midpoint is somewhere in between Euler and Runge-Kutta. A Dorman Prince is what a lot of people use in neural ODEs. So that's basically the difference between the two is that in fixed step size solvers, as I said, user needs to decide when to evaluate when to evaluate the derivative function, and taking a step, the next step, right? Like y1 to y2, y2 to y3, which means that you need to explicitly tell the ODE solver program the delta t, like how small you want the steps to be. Like if you want your time step to be like 0.1 or like delta t to be 0.1 or 0.01 or 0.001. It depends on how much time you got and how much accurate you want your solutions to be. Compared to that, adaptive step size solvers, the algorithms decide when to evaluate f and take a step. So instead of you giving delta t, algorithm will decide. And basically the high level idea is that if at some region there is smooth dynamics, for example, like if your solution looks like looks like this, then at this region, there's barely any dynamics. There's barely any change. So in this region, you'll take large steps. You'll go like boom, 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 and then. But in regions like this, it has very fast changing dynamics. So in this case, you don't want to go like this and this and this, right? So that would be a bad idea. So you want to take very small steps like this, like very small steps, small steps, small step, like doing a gradient descent basically, right? So that's basically the idea. So internally, I'm not sure how they actually work because I haven't taken a look at the source code. But it has some like if and else's. So it internally checks its solution, and if it is not satisfied with the solution, then it'll go back and then take another step and something like that basically. So it's a bit more complicated than the fixed step size solvers. But internally they use like either this or this. Like Dorman Prince will certainly use like RK4 to take some step, and then if it's not satisfied, it'll roll back and then take smaller step, and compare basically. All right, so yeah, before we end the differential equation primer, there's also like second order differential equation, and just short introduction. So the general form of second order differential equation would look like this. So some function, actually this should be all like pyt, qyt, ryt, and gyt. Yeah, I'm sorry about that, but yeah, this is okay, rather general form. And usually we don't deal with this because this is already too hard to deal with. It's just hard to solve this analytically. So the only thing we can do is probably just a numerical solution. So usually what we see in physics problem is these things. So either it's homogeneous or it's non-homogeneous, or there's some non-constant term on the right-hand side. And yeah, of course, second order differential equations can be solved numerically as well. All right, so moving on to Neural ODE now. So we'll first take a look at the ResNet, because ResNet is kind of the motivation for coming up with Neural ODE, or at least it was written that way in the paper. So just a refresher. So ResNet, the next hidden state, or the next latent state is determined by some value, some nonlinear activation function, and on the weight matrix, the bias, and then the residual connection here. So this is typical, your typical nonlinear layer. Actually, let me erase that. So this is your linear layer. This is your linear layer. This is your nonlinear function, nonlinear activation function, and this is your residual connection. Right. So this is your ResNet. So hope this is pretty much clear to everybody, and we're gonna abstractify. I'm not sure. Yeah, we're gonna abstract this away into this form. So it's just some function, basically. It's just some functions. And we still need the current latent state at time t or layer t, and you still need this weight, which is just your weight matrix, and the bias. So we still need the parameters, and this is some function representing. It could be a linear function, it could be nonlinear function, whatever, some function basically. And you still have the residual connection. So what we're gonna do is we're gonna rewrite this in a couple steps. So first of all, we take this, move it over here, so we get this guy, and this can be rewritten as this. This is divided by 1, so it doesn't make any difference, right? Dividing by 1 doesn't make any difference. And we take a look at this guy. So take a look at this, and then change this to delta, and delta equals 1. So nothing still changes. It's the same here and same here. And now what we do is we take delta and push it to the limit 0, and you see this guy. And what is this guy? What is this? This guy is exactly the derivative. It's the differentiation of the function h, or the latent state h. So h is written as a function now because we're doing a derivative. So this is your final. This is like rewriting ResNet as a form or some other form, basically some like continuous form, because ResNet is a discrete. It has a lot of layers, so it has discrete layers. But by pushing the gap between layer into an infinitesimally small value to 0, you can actually make it into a continuous neural network, basically. So that's what this means. So you want to compare between this guy and this guy. So here you can also see that theta t is now just theta, because what you're saying is the rate of change of your latent state is dictated by some nonlinear function, and the function doesn't change. And the function, the theta is fixed, and now the function receives t now. So it's a bit more like in the ODE format. So let's take a look. Let's compare between the two. So this guy versus this guy. So this guy has L discrete layers, like ResNet 50 has 50 layers, ResNet 100 has 100 layers. This guy doesn't have a discrete layer. It has an infinite number of layers. It's a continuous architecture. So it's a different paradigm. And the latent state changes discretely, which means that once you move from one layer to another, it'll change. It'll make a sudden like change. Like it'll look like the state will change in a discrete manner over different layers. But this guy, the latent state changes continuously, because what you have is a rate of change of the latent state over time, and you just simply need to integrate it to get the change, right? Right. So the latent state dynamics, how the latent state changes is controlled by L different number of functions, which means that there's layer number 1, layer number 2, layer number 3. So this is L1, L2, L3, all the way to L50 if we're talking about ResNet 50. So 50 different functions. So latent state dynamics controlled by 50 different functions. But here, latent state dynamics controlled by just one function, this function, which is the ODE dynamics function, right? So you can see the clear distinction, the comparison between the two. So all neural network models follow this format, but actually now we can generalize it, or not sure if this is generalizing it. This is because it is in a way a bit more limiting, but we'll talk about that later. But anyway, so this is a different paradigm, different way of viewing neural networks. So this is interpreting ResNet viewing ResNet as a ODE. And we talked about vector field. So this is the vector field in ResNet. So this is depth 1, depth 2, depth 3, depth 4, depth 5. And your vector field it is discrete. So at each layer, it has its own vector field, or how it changes the latent state. But here in the continuous format, it has a continuous vector field, basically. So yeah. Moving on. So we can actually apply the same logic to recurrent neural networks as well. Not just ResNet, but also recurrent neural networks, RNN. We're just going to look at the vanilla RNN, not just the GRU, so just the RNN. So in RNN, the next time step hidden layer is dictated by this formula here. So this is the equation. So there's nonlinear function, activation function, such as tan-h, and then there's U for linearly transforming the previous hidden layer, and W for linearly transforming the current input and the bias vector. You can actually, assuming that U is identity function and F is just a vector of ones, then you can rewrite this function into this equation into this equation. So here, so U is gone, F is gone. So you have this, and then you can put this guy into the back. So this is this guy. You can rewrite this like this, and now you have differential equation here, like this. So this guy is now this guy. So your next time step hidden layer is current time step hidden layer plus some change, which is dictated by this function here. And this function consists of inputs, the current time step, and the current new input. the t, the time step, and the theta, which is the weight matrix and the bias. Right. So you can use neural ODEs to actually deal with time series data as well, or sequence data actually. And when it comes to continuous time, handling continuous time, neural ODEs does it better than recurrent neural networks, because as you know, RNNs are inherently a discrete sequence processor or discrete sequence encoder, as opposed to continuous time series processor, which is neural ODE. All right, so this is the formulation of neural ODE. So you have the function, you have some derivative function, or the rate of change of your hidden layer or latent state, and this is now a neural network. Before, if you can remember, in free falling object, Fyt was what? It was mg minus gamma v, right? But in neural ODE, what we're saying is we don't know this. What we do know is we're just gonna model the differential, the derivative function with neural network. That's why it's called Neural ODE. So we're no longer given an analytical form of the derivative function. We're just gonna use Neural ODE to model this. So what is the meaning of this in terms of ODE? That means that we have an ODE. We know that some problem, for example, image classification or time series classification or translation, whatever, we know that that problem can be viewed as an ODE problem, or actually IVP problem, to be more precise, to be more correct. So we have an IVP problem, and we don't know Y prime. We don't know the dynamics of that problem. We don't know how to do image classification, or rather, we want to do image classification, but we don't know how to change the input, or we don't know how to the rate of, we don't know how to define the rate of change of the input in order to successfully do image classification. That means we don't know Y prime, but we want to learn Y prime from data via neural network and backpropagation. So neural network being this guy. So we want to model the derivative function using neural network, and then we want to learn it in a way that it will successfully help us do the task, whatever the task can be. So that is the spirit of Neural ODE. So this is a typical example, which is a spiral example. So what we're doing is this here, this spiral is the true data. It's a true sample. So we have a task which is to learn to fit this spiral data, and we want to use a Neural ODE to do that. So that means that we don't know Y prime. We don't know how the spiral changes over time. We don't know what the dynamics of it. So but we have data. We have a lot of spiral data like this. We have a lot of different spiral data. So what we want to do is we want to use those data set to train this guy to fit this nicely. So as you can see, this is like epoch 1, this is epoch 2, epoch 3, epoch 4. This is epoch 1, epoch 2, epoch 3, epoch 4. So as you train your dynamics function, which is a neural network, as you train it using backpropagation, so you can see that it is fitting better and better and better and better to the true spiral, true time series. So that's what we want to do with Neural ODE. So once we have learned it, then we can use it to go further into it, or maybe go outwards like this. So you can guess how the data or how the HT or YT, to be honest. So yeah. Once we have Neural ODE, fully trained Neural ODE, we don't know the true YT because we don't have the analytical solution to the YT. But what we do have is we have a well-learned Y prime T. We well-trained Y prime T. We do have this. We don't have this, but we do have this once we've trained it using data. Then once we have this, we can just simply integrate it over time to go further in or further out to see how y will change over time. Just like calculating velocity at a certain time step t, we can see where the trajectory will be at certain time step t. It's just that we don't do it analytically, we do it numerically. So that's why we want to do neural ODE. So yeah, so in order to do that, we need to see how we can train or update the parameters of this guy, parameter being this, right? So let's take a look at this. So the input state, or the input to the neural ODE model, is H0, which is the initial time step. So it's still IDP, so we still need initial state. And state dynamics, or the derivative function of ht, dht dt, which is this. Yeah, sorry. So yeah, the rate of change or state dynamics is this, and we are gonna represent this as a neural network, which is typically just a multi-layer perceptron with some hidden layers. So it's a feed-forward neural network with 1 or 2 hidden layers with, like, you don't know, like 10, 20 hidden neurons, or maybe 100 neurons. It's relatively a small sized neural network. So that's your MLP. And the output state, so your output of your neural ODE model would be HT, which is the last time step, capital letter T, can be written as this, as I've shown you before. So H is just H0, which is your initial state, plus integration over time. And since we don't know how to do it analytically, we can do it numerically using ODE solver. So it could be Euler solver, it could be Runge-Kutta solver, it could be Dorman-Prince solver, whatever. And the argument to that program or the function is your initial state, your dynamics function, and your dynamics function parameter, and your initial time and your final time. And actually, I also forgot delta t here. You still need delta t somewhere. I mean, if you are to use Euler solver, if you are to use the fixed step size solver, you need delta t. If you're using adaptive step size solver, you don't need this. All right. So let's take a look at the model architecture. So let's say that we're going to do image classification with neural ODE. So obviously you want to have some image. So this is your input image, and then it's probably a bad idea to use directly neural ODE on top of this. So you want to encode it, because this could be like 128 by 128. So it's like about 16K dimensional input. And currently, neural ODEs cannot deal with this level, this high dimensional input. So you want to encode it or compress it into a several hundred dimensional inputs, like 100 or 200 dimension or 100 dimension, something like that. So you want to use CNN to compress your image into maybe 100 dimensions on the output, so 100D. So CNN, you still need to learn CNN though. So this is still learnable. It's a learnable CNN. It's a learnable concept. But what we do is you just compress your high dimensional feature input into a lower dimensional feature. So that becomes your initial value in perspective of neural ODE. So this becomes your H0. And then you use some program to solve it. And then you get HT, the capital letter T. And then that becomes your final representation of your image. And then once you have your final representation or latent representation, you use softmax layer to classify it into, hopefully, a dog. So that is your neural ODE for image classification. If you're doing time series line fitting, if you're doing time series like mean squared error type of update, then you have this time series data. So like the dots are your observation points. So you have these observation points, and then, for example, let's say that let's say that at this particular example, you start from here. You start from this particular example here, which is 2-dimensional input. So it could be like, if this is your Cartesian coordinate, this could be like 2.0.5, like 2,0.5 or something. So that becomes your input. So your H0 is a two-dimensional coordinate input, and then you solve it with ODE solve like this. And note that there's a difference here. Here the difference, this is 0. Here in the image classification, your time step input is 0 and t. But here in time series, your input time steps are 0, 1, 2, all the way to t. And your program, your ODE solver program, whether it is Euler solver, or whether it is a Dorman Prince, whether it is Runge-Kutta, you dictate what kind of outputs you want to obtain from that program. So if you dictate like this, then what you get is you only get H0 and HT. If you feed this argument into your program, then you will get H0, H1, H2, all the way to HT. And why we do this is because we want to backprop. This is a time series. So this is image classification. So you don't need any intermediate. You don't need H1. You don't need H2. You need only the latent state of you need only the final latent state so that you can do classification and then backprop. But here in time series, you want to actually, yeah, we should have started from here. So I'm sorry about that. Not here. We should have started from here, because we're moving inwards like this. We're moving inwards. Anyway, so as I was saying, if you're doing time series, then there are multiple observation points, and you want to hit all those observation points, H1, H0, H1, H2, or it could be even H1.1, because we're dealing with continuous time. Could be H1.1, H2.7, could be H3.414567. Doesn't matter, as long as it's all up to you. Like at which time point you want to evaluate your H or your state, it's all up to you. So you just need to define that here in one of your arguments, actually. So once you have H1, H2, H0, H1, H2, you want to hit all this correctly. So you want to take all this and then do mean squared error between true. So I'm just gonna substitute this y0 with this will be your y hat, and there's also y0, your y hat 1, true y1, y hat 2, true y2. So you want to hit all these correctly and then do it and then calculate the mean squared error over all the observation points. And that's why you want to take a lot of time steps. You want to feed a lot of time steps to obtain this, and then do mean squared error over all observation points. And hopefully you will get a nice looking thing like this, basically. All right, I hope this is pretty clear. This is pretty important. Like this is the only difference between the two, here and here. But that tells a lot, like depending on what kind of task you want to do. Yeah. So parameter update. So this was forward propagation, and so you do forward, you do backward, and then you update the parameter, right? So now we want to do update. Now we want to update the parameter, and we need to update this theta so that f learns the correct dynamics. So far, we didn't really know if f was learning a correct dynamics or not. It's because f is usually an MLP, randomly initialized, right? So we want to update that so that it conforms correctly to the given data's dynamics. So you want to update theta here, which is here. You want to update this. And if you want to update this, that means we have to backprop through ODE solver, the program, because theta is just a argument to this program, ODE solver program or function. So we need to, in order to update this and also update this for this particular example. Here, we don't have an encoder, but here we have an image encoder. So we not only need to update this, but we also need to update this guy as well. So in order to do that, we need to go full backprop all the way here. So can we do backprop? Can we backprop through this program, ODE solver? That's the question. And it turns out that for some solvers, we can do backprop through them. So Euler's method, we can backprop, because Euler's method is, after all, just a I'm sorry about this. Yeah, Euler's method is just simply another form of gradient descent. It's just taking a fixed delta t and then evaluating your function and then summing it up. So basically, your Euler's method is nothing but just multiplication and addition. That's it. So there's no reason we cannot do backprop. So if we're doing Euler's method, it only involves multiplication and summation. This is like actually more precise, add up. So add multiplication operation and add addition operation. So we can definitely go do backprop through Euler's method. And in the same manner, we can also do backprop through Runge-Kutta, because Runge-Kutta is just doing Euler's method 4 times in one step. So that also involves just multiplication and addition. Dopre 5, I'm not really sure. I haven't, my memory, if my memory serves me right, Dopre 5 does involve if and else, but PyTorch is pretty flexible. So even if you use if and else, you can still go do backprop through Dopre 5. So I think, yeah. So for some solvers, we can backprop. So these are the ones that you are kind of like, you can achieve good results by doing backprop through these solvers. Some other solvers is probably not a good idea. So I introduced some other solvers in the previous slide, right? And some slides ago. So for some other solvers, it's probably not a good idea because it's numerically unstable. So it's like pretty complex, involved ODE solvers. They probably have a lot of like, very intricate working parts. So you don't want to do backprop through them. It'll be numerically unstable. So in that case, what can we do? Like if we want to use some solver that is not friendly towards backprop, what can we do? So actually, yeah, not just that. Actually, doing backprop through this these solvers are friendly towards backprop, but they also have their own problems. So this has their own problem. This also has their own problem. Let's take a look at that first. So we're just gonna ignore this for now. So for some solvers, we can do backprop, as I said. So here, these two are the fixed step size solver. This is a adaptive size solver. So as I said, for these two solvers, we need to set the number of function evaluation. Function evaluation meaning that you need to evaluate your derivative function and then calculate the slope, meaning that you obtain the slope or the gradient, and then you take a small step towards the gradient. In Dopre 5, Dorman Prince, the solver adaptively adjusts number of function evaluation for you, so you don't need to worry about that. But given this knowledge, the more NFV, the smaller step we take, or the more number of function evaluations we conduct, the more accurate the solution will be, obviously, right? So like doing gradient descent, the smaller step we take, the more accurate the solution will be. So what happens if number of function evaluation reaches like 1 million times? What would that mean? What does it mean to take 1 million small time steps to achieve a very accurate solution in your very accurate ODE solution? What does that mean? That means that your VRAM will explode, because 1 million number of function evaluation and then doing backprop on that is like having a 1 million layers in your ResNet. It's the same thing. So we're doing backprop through Euler's method or Runge-Kutta. If we're doing Runge-Kutta, it's even worse, actually. So, but let's just abstract everything away. So we have an ODE solver, and we do number of function evaluations 1 million times, and we're doing backprop through that. That means you are going through 1 million layers of ResNet. So, and 1 million layer is surely it'll explode your VRAM, because you can't contain all the activation values of your 1 million layers in your VRAM. So that's just impossible. So that's a problem with backpropping through these solvers. And yeah, ResNet is only 50 layers. And do you really want to do 1 million layers? That's just crazy. So how can you use Neural ODE without using too much VRAM for backprop? So how can we avoid doing backprop through these solvers and still train your theta, your derivative function parameters? How can you do that? So that's when Adjoint sensitivity method comes in. So the Neural ODE paper in Europe 2018, the best paper, which got the best paper, the contribution of that paper is actually this part. People already kind of knew that neural networks could be viewed as ordinary differential equations, and they already knew that they can use backprop to train the derivative function. But then it is not scalable because of this problem. So the authors of the original Neural ODE paper in 2018 Europe, they came up with this technique to avoid that problem and still be able to train your Neural ODE model. So here, before we jump into this, what do we need to actually update the parameters? So we need this basically, right? So we need this, and we also need this. So this is the gradient of the loss with respect to the input state. So we first need this in order to do image classification. We just need this. In order to do time series, we need this actually. We need all the intermediate observation points. So the adjoint the spirit or the high level explanation of adjoint sensitivity method is using ODE solver. So we in the forward prop we used ODE solve to do that, right? We use ODE solve to do forward prop, but in back prop, instead of doing back prop, we use something called adjoint sensitivity method, which enables us to use ODE solve again backwards in time to obtain this backwards in time. So given HT, because we do know this, because HT is the last layer just before the softmax layer, right? So we do know this, we can calculate this, but the problem is we start from here and we need to go back all the way to H0, right? And in along the way we might need this as well. So along the way we might need like H1 all the way to like some HT basically. So we can start from here, and then using something called the adjoint sensitivity method, we can work our way backwards all the way to the starting point. And in doing so, we use ODE solve again. The same program that we use to solve forward process, we use to solve this guy and this guy. So we use the same Runge-Kutta 4 or Dopre 5 or Euler's method. We use that again. So that's basically the spirit of adjoint sensitivity method. I'm not going to go into detail how we can derive that. It's just very mathematic, not too much involved, but it involves like a Lagrange multiplier and all that. So you can look it up. You can look up the original paper if you're interested in that. But basically, as I said, the spirit is use ODE solver again, but backwards through time, starting from large T to the point 0, time step 0, and then obtain this guy and this guy. We need one more thing, actually. We need this to actually update the parameters of the derivative function, right? We definitely need this. Not only this, but this. So this is gradient of the loss with respect to dynamics function parameter. And how can you obtain? So these we can obtain with the adjoint sensitivity method. This, how can you obtain this? What we do is we solve this guy and this guy at the same time, together at the same time. So when we call ODE solve backwards, to obtain these guy, we also plug in some additional variables to obtain this at the end. So we can just do it in one go. So this is your final algorithm, adjoint sensitivity method algorithm. So it's a reverse mode derivative of ODE initial problem. So IDP. So it's a reverse mode. So you set up a certain like a variable. You pack these information into the variable, and then set and put this, and also you obtain this OG dynamics, this guy. You set this function OG dynamics, and then put this here, and put this here, and then call ODE solver backwards. So you start from T1, and then you go to T0, and then you have the theta, which is the derivative function. Derivative function is parameter, and then you obtain this. Because once you solve ODE solve, you will get this guy. You start from here. And then you're solving backwards, so you obtain this afterwards. But along the way, you get these and this guy at the same time. So this is what you want. This is what you need to update your CNN encoder and your derivative function parameter. So that's how you do adjoint sensitivity method. So in overall, what you do is you do one ODE solve in forward. So ODE solve, you call ODE solve in the forward process. So forward prop, and you do back prop. So you just need to call ODE solve once and twice, and then you can update your model, entire model, without doing any back propagation at all. So this is back propagation free. You just, so this means that you're approximating this value through solving ODE backwards in time. So this is approximation. So obviously these values, these gradient values that you obtained by doing adjoint sensitivity method will be less accurate than doing a full backprop, because this is a approximation to the backprop value. You're not doing the backprop you're not doing backprop very accurate. Technically, you're not doing backprop because you're just approximating these value using adjoint sensitivity method. So using backprop will actually give you better performance than using adjoint sensitivity method. But then again, if you use adjoint sensitivity method, you can save all the VRAMs because you don't have to do backprop. So there's a trade-off there. Right, so some experiments. So this is doing image classification, specifically MNIST classification. So this is the baseline is 1-layer MLP, ResNet, RKNet, which is RKNet is just ODE with backprop, ODE plus backprop. ODENet is ODE plus adjoint sensitivity method. So you can see that this guy uses constant size memory because it's not doing any backprop, so it's using constant size memory. This guy here is doing backprop, so it is using some number of, it is using linearly increasing amount of memory. And the ResNet, of course, our ResNet will also use memory, which increases by the size of the layer. Here you can see L tilde because there's tilde here because you decide how many time steps you want to take. So that's up to you. And you can see the test error. So ResNet is about achieving only 0.41% error, and ODENet is achieving 0.42% error. So the performance is pretty comparable, but that's only MNIST classification. If you go to ImageNet, then ResNet outperforms ODENet. ODENet is nowhere close to, I won't say nowhere close, but it's definitely worse than ResNet. So what ResNet still is, so yeah, I mean, yeah. MNIST classification is a simple enough task, so ODENet shows like comparable performance with reduced memory footprint. But if you go to like larger scale tasks, then ODENet, neural ODEs are not ready yet. So it's not as practical as ResNet now. And people are working towards it, like how to make it practical, how to make it scalable. So it's an active topic of research these days. This is the statistics of ODENet. So when you train it, the number of, this NFE is the number of function evaluations, basically how many steps you take. And interestingly, you can see that when you're doing forward and the backward, you do more function evaluations when you're doing forward as opposed to when you're doing backwards. So that's interesting. So as I said, you do one forward prop and you do one backward prop. So you call ODE here, you do ODE once, and you call ODE twice here, and you can see that when you go forward, it takes more number of function evaluation as opposed to going backwards, which is kind of interesting. Yeah, and as you train your model, your number of function evaluations in forward, this here, increases. So that means that your ODE your derivative function dy dt is learning more complex functions over time, because the more complex means that the more complex the function, the more number of function, the smaller time step you need to take to obtain accurate solutions, as I said. So this kind of like indirectly indicates that as you learn your model parameter, oh, I'm sorry. Yeah, sorry about that. So yeah, as I said, this graph indirectly tells you that your model is learning more complex function over time. You can also do a sequence to sequence with ODE, actually. So this is the very first sequence to sequence model using ODE. So it is using RNN encoder and ODE decoder. So there's some sequence information put into the RNN encoder. So you have some sequence of observation points, and then you compress it into a hidden layer, and then you can actually do variational autoencoder style. So this is like a VAE, but using sequence models in both encoder and decoder side. So if you remember VAE, the VAE output, the intermediate layer of VAE is just the mu and sigma, which is used all involved in like reparameterization trick. So you encode your observation, sequence of observations, and then you encode it into a fixed ZT0, and then using ZT0, you start decoding it using Neural ODE. So you integrate it with ODE Solver over time. So that's how you do ODE sequence to sequence. And using this, you can actually try to learn a spiral. So using sequence to sequence, perform interpolation, extrapolation. So here, the green lines here, actually, let me use actual green line here. So green line here is the ground truth. And the blue dots here, the blue dots are the observation points given to the model. So you encode these blue dots into the encoder, RNN encoder, and then you try to interpolate meaning that you try to fill in the gaps between the observation points, like here, here. That's the interpolation. And extrapolation is you keep on going like this, even after the final observation. So using the ODE sequence to sequence, the authors did spiral reconstruction or interpolation and extrapolation. And you can see that it is doing a much better job than RNN, actually. So RNN kind of understands what it wants to do. So the red is the extrapolation. So RNN kind of understands that it is a spiral and goes like this, and maybe moving in a circle. But if you use ODE, then it is doing a much better job. Like it exactly understands the dynamics of this spiral. So it knows how to do extrapolation as well. So it's in this kind of like continuous time step, like if you're handling continuous time series data, neural ODEs are a better alternative than RNNs. But then again, neural ODEs are not scalable enough yet. So like in practice, RNN outperforms neural ODE in high level, like high dimensional data, actually. So, but then some like researchers are working really hard to make neural ODE, whole neural ODE very scalable. So sooner or later, it'll show like similar. I expect that sooner or later, neural ODE will show similar performance or even better performance than RNN in a lot of like time series modeling, time series handling tasks. Yeah, all right. So the conclusion is that neural ODE is a new deep learning paradigm, or new neural network paradigm, actually, or new machine learning paradigm. And it's a great alternative to RNN when handling time. And the pros of this whole thing is that you can use a well-known guaranteed ODE solvers, like, because as I said, there's like whole long like history of ODE solvers and ODE solving techniques in mathematics and physics. So you can borrow their knowledge to do like very, very powerful computation. And a lot of modern ODE solvers guarantee some error tolerance. As a parameter to the program, you put a error tolerance like 10 to the minus 5 or 10 to the minus 7, then the solver will guarantee that amount of error margin. And as I said, yeah, so there's a rapid development these days. It's a hot topic these days in machine learning community. All right, so yeah, this is the end of today's class, and actually the last class of this entire semester. So thank you very much again for participating in this class, and I hope you guys learned a lot, and hope you guys are ready to do AI research. Thank you very much, and bye-bye. Oh, by the way, this Thursday, well, not Thursday, but the practice session will consist of implementing the Euler solver, the Runge-Kutta solver, and actually implementing Neural ODE yourself, and then training your Neural ODE on spiral data, and then trying out different solvers like adaptive solvers and adjoint sensitivity methods. All right. Thank you very much. Bye-bye.